continuing with the intermediate value theorem, now let's state the classic, make the classic statement of what the intermediate value theorem says. So what we came to as a simpler problem than two interesting curves crossing was one interesting curve and seeing if you can guarantee that it crosses some horizontal line. Okay, so what we have, let me just clean this up a little bit. The situation we're going to have is we have f of x, that's a continuous function, and it doesn't necessarily have to be continuous everywhere, it just has to be continuous on the region we're interested in. So let's say we are analyzing it from x equals a to x equals b, so that's, let's say, on the closed interval a, b, including the endpoints, that's important. So it's continuous all the way from the start to the end of where we care about it. And we notice that it's crossing, or that it starts out below a certain level y equals n and ends up above, or vice versa. So we have that f of a is less than n, and f of b is greater than n. And it would work the other way as well if it went from above to below. But let's just do this case. Okay. Then what can we conclude? That it must eventually cross that level. So there's nothing special about n except that it's something that we change sides of from between the start and end of this interval. So if these two things are true, then there must be some crossing, and we just want to talk about that explicitly, just name it. There must be some, let's say, c in that interval where it crosses that line that we've noticed that it seems like it should cross, and that just means f of c is equal to n. And so notice what we've done. We've asserted that there's a solution. There exists some solution to a certain equation involving this function f. And that solution would be x equals c. Okay. So let's get that out of there. Okay, so that's the classic statement of the intermediate value theorem. And it also works if you start out above and end up below. Nothing else is different. Okay. So I'm not going to prove this for you, that if you look at a technical, careful definition of continuity, which a lot of beginning calculus courses don't present to you anyway, you can prove completely rigorously that this is true. It's not something that most people find to be implausible. Again, though, I want to focus just for a little bit before we go back to our more complicated example. How could this fail? And why is continuity a necessary hypothesis, a necessary condition for this? And also point out why that in many cases that's not likely to have that fail. So what if this were, for example, let's say this is time, and this were like position, so let's maybe still call it y, but just say position as a function of time. And so I often do an example of somebody's driving on a straight, like essentially north-south road, and let's say y is how far north or south you are from some origin. And what would it look like if I started out south of some particular location on the road? That's going to be our n. And I end up north of it as time goes by. It would be something like this. And I don't cross, let's say. Okay, so I come up like this, and then suddenly I have to jump over. And then maybe to just make it more definite, maybe like open and close there. Okay. This is the kind of function that would avoid having any solution to f of x equals n. There's no value c, there's no value of x at all in this interval that matches. And of course what we see is that it did that by being discontinuous. So in this case of like position versus time, what kind of behavior would that describe? It describes something very unrealistic, and it would be some sort of car driving along the road, and then it instantaneously teleports like 5 miles further north, and then goes on its merry way. The only way you can go on this road and avoid seeing every point between on the road is by teleporting. Okay, so I talk about that. That's why that's the the physical meaning often of this assumption of continuity is that you can't have things like teleporting cars. If you don't have a teleporting car and you go from south of some point on this long straight road to north, you're going to hit every point in between. Fairly intuitive. Okay, so the next one, the third part, I'll go back to that very explicit problem with ln x and x e to the minus x and show how we can very, very carefully use this theorem to show that there must be a solution to that equation.